I want to welcome everyone to the 2015 edition of the SU Research Day and Innovation Showcase. This is our third annual edition of this particular event. We appreciate everyone being here. Special thanks to our provost, Dr. Diane Allen, who is on her way here from a meeting at the system office, so she should be here, she said, in probably 15 or 20 minutes. So special thanks to Dr. Allen and the rest of the exec staff and the president, Dr. Janet Dudley-Eschbach, for her support of this event and research and scholarship on this campus. We really appreciate everything that they do for us. For our next presenter, we have Dr. Stephen Habay from the chemistry department here at SU. The title of his presentation is Adventures in Undergraduate Organic Synthesis.
Thank you. I want to thank everybody for coming out today, and I want to thank my dean, Karen Olmsted, for the invitation to talk today and tell you a little bit about what's going on in the chemistry department and in my laboratory. So there's a few pictures up here of some of my students over the years, and I want you to take a look at these people because these are your future pharmacists, future physicians, future scientists, and dentists, and they really need to be capable people, and they really need they do, right? They're going to take care of us. And so, there's something about undergraduate research that I think is really valuable for a college education. And there's something that adds to just classroom teaching that you really, really need. And I think it is one of the most important parts of a student's education here. And so, although we want to train students, I want to also have very good, very interesting problems for them to work on. That I think are important. And so I'm a synthetic organic chemist, and what that means, or the way I think about that, is I think of myself as kind of a molecular engineer. I like to build molecules the same way that a regular engineer or an architect would build a building or build a house. Right? You take raw starting materials and you combine them together piece by piece until you've achieved your target structure. And that's exactly what we try to do in the lab. So I want you to think about molecular structure as a type of sculpture, as a type of art. And we're putting these things together the same way that you would something that you can actually see with your eyes. So I have a molecule up on the screen there that's rotating. That's Taxol. It's not a molecule that I work on, but it's a very well-known anti-cancer compound that is used predominantly for ovarian cancer. And if you look at this thing, I look at this molecule and I see how complex it is and how wonderful its structure is and all the little details that are present there. So in terms of thinking of these structures as art, right? Humans are very good at making different types of art, making paintings, sculptures, architecture. And I think of molecular structure in the same exact way. And just to give you an idea of some of the beauty and some of the complexity of molecular structures in nature. This is just one example where we have Streptomyces, which is a type of bacteria. And this stuff is a molecule factory. It builds some of the most beautiful, complicated molecules known to man. These are all antibiotic molecules. So this thing is under constant attack by other microorganisms, and it constantly produces these chemical weapons to protect itself. And so humans are trying to weaponize these molecules against microorganisms themselves, to use them as antibiotics to prevent microorganisms from invading our bodies. And so if you look at the picture on the right there, you'll see these blue droplets. This is literally antibiotic that is being oozed out of these bacteria. So it's producing this blue-colored antibiotic. And so if you think about humans as very good artists, making very beautiful things, you can think of other living organisms like bacteria, like plants, that can make beautiful structures as well. And so I want to talk about two different projects that are going on in my lab and give you a little bit of an idea of how we do organic chemistry, or how organic synthesis takes place. And so just as you would build a building or build a piece of sculpture, you have to have some kind of plan in place. And so when we come up with a project, we have a target molecule that we want to make. I'm again using Taxol as an example here. You need to have a plan. And so you're going to break this molecule down piece by piece into tiny little fragments of things that you can buy from a chemical company or that you can make in the laboratory, and you're going to assemble these very small pieces one step at a time until you've built up the molecular structure to the exact target that you want. And this is really tricky because you have to not only assemble the pieces but get every single atom pointing in the exact direction in space that you want it to go. And so this is a very, very challenging thing to do. And so it really does start with mixing chemicals in a flask. So we are mixing the chemicals in the right amounts for the right amount of time at the right temperature, and the molecules just click together. I don't do any of the work. I just put everything in a flask and the molecules know what to do, right? And these things are not alive, right? They're just tiny fragments, and they know how to click together to form new bonds, new molecules. And so once we make our new molecules, we have to isolate them, and that's where we spend a lot of our time. We have to separate the molecules from the mixture. And so we use techniques like extraction. And then we remove the solvents by using an instrument called a rotary evaporator. And after that, we get this goop, or this solid stuff that we have to then purify to isolate the final compounds. And so you can do this by hand, or luckily we have an automated instrument in our department that does this for us, so we can just inject our goop into this instrument and out pops a pure molecule at the end. And then since you can't see any of these molecules that you make, you have to have a way to identify them. And so we use largely this technique called NMR spectroscopy, which is the base technology behind MRIs. So if you've ever had an MRI, you have basically been in an NMR instrument. You were the sample that went into the instrument, right? And so we don't get an actual image of the molecules out from an NMR, but we get something called a spectrum. And so we teach our sophomores how to interpret these graphs so that they can identify that we did indeed make the correct molecule. And every molecule has its own unique spectrum. So if you learn how to interpret this information, you can prove without doubt that you made the correct molecule. And so this is what you do. But the thing that you have to remember is you have to do this for every single step in your synthesis plan. So you do one chemical reaction, you go through this cycle. Then you do the next chemical reaction and you go through this cycle over and over again until you've reached your final product. And it's a lot of work, but it's also a lot of fun too. Now, I wanted to talk about two projects. The first project has to do with drugs that interact with the brain. And so I've been interested in drugs that interact with the brain for a very long time. And what I found out through the years is that there are a lot of biomedical researchers that are doing really great work and trying to understand different diseases, different conditions that exist in the brain, like Parkinson's or Alzheimer's or migraine headaches, and trying to find ways to help treat these diseases. And so they really need access to drugs and pharmaceutical compounds in order to do these studies, in order to understand how these diseases work. And the problem with using these drugs is that they're really, really expensive. So a few milligrams of a drug can be over $1,000. Okay, so these things are really, really expensive. So what they really need are collaborators that are willing to spend time and resources making these molecules for them. So biologists and biochemists are not organic chemists. They don't make molecules. So they need a collaborator that will do that. And that's one of the things that I am trying to do. And so I got interested in migraine drugs, and one of the new classes of migraine drugs that are coming through the pipeline now, there are none of these that have come to market yet, but these are called CGRP antagonists. And these molecules basically prevent blood vessels from dilating. So one of the causes of migraine is that you have blood vessels in your brain that dilate or expand, and that irritates nearby nerves, and that causes the pain from a migraine. And so if you can shut off this blood vessel dilation, you can prevent the nerves from being irritated, and so you can effectively shut down all the symptoms of migraine. And so I was looking at some structures to make here, and I was at a faculty mixer a few years ago between the chemistry and the biology departments, and we were standing around drinking coffee and eating cookies and talking to each other, and I went around kind of like a drug dealer, like, hey man, you need anything? I can hook you up, right? And so, sure enough, one of my colleagues in biology, Victor Muriel, he's a vascular biologist. and he is studying blood vessel dynamics. And so he asked if I could make this molecule that you see on the screen here. And don't worry about understanding the structure of the molecule. Just take note that it's a pretty big molecule. It's kind of complicated. And he asked if we'd be able to make this stuff. And we started looking into it. And so there is a published recipe for making this drug. And so we started working on that published recipe. And we soon got very frustrated with it. It's like any of those bad recipes that you try in your kitchen and they just don't turn out the way that you think they will. And so all these problems started popping up. Yields are lower than expected, side reactions, we can't find data in the papers, and so all these problems. So we just got frustrated and we decided, you know what, we're going to try to come up with our own way of making this molecule. And so that's what we did. So we decided that we were going to break this molecule down into smaller pieces that we could assemble or buy and put them all together to make the final structure. And so we spent a little over a year doing this, and we've been successful. We finally made the final compound, and we've been able to give Dr. Muriel some of that compound to test right now. And so I just wanted to summarize what we've been able to do with this particular project. First, we shortened the synthesis from 15 to 11 steps, so we saved 4 steps worth of work. We were able to boost the overall efficiency of the synthesis by over 30%. We eliminated pretty much every side reaction that we encountered in this process. We're filling the data gaps, pieces of information that are missing from the literature. We're finding those pieces of information, and we hope to provide that information to other researchers that want to make this drug. We made the synthesis scalable. We can now make gram quantities of this drug instead of milligram quantities of this drug. So it's operationally simple. One undergraduate can spend a week in the lab and obtain a gram or 2 of this molecule. And it's cheaper. So we haven't done a cost analysis on this compound, but I can tell you our annual research budget within the Department of Chemistry is a few $100s a year. And so if we can fully fund this project from internal funding from the department and the Henson School, people with more resources should be able to accomplish this same type of thing. So we hope to publish all of this information soon and make it available to people, other researchers that are interested in this molecule. It is an important molecule. It's used in all kinds of different studies having to do with vasodilation. And any leftover compound that we have available, we plan to make available to people for free. So if you know anybody that needs any of that drug, have them contact me. We'll be happy to give them some. The other project that I wanted to talk about has to deal with a class of molecules called alkaloids. And all of you, I am certain, are familiar with what alkaloids are. These are organic molecules that contain nitrogen. So anywhere you see a capital letter N, that's a nitrogen. And so one of the most famous alkaloids that everyone, or most everyone in here is probably familiar with is caffeine, right? And these are natural products that are produced by organisms, most of the time by plants, but also microorganisms, marine organisms can make these molecules. And so there have been so many different alkaloids that have been isolated and synthesized over the years, right? Morphine has revolutionized medicine as a painkiller. Cocaine is a stimulant that everyone knows about. Quinine is an anti-malarial compound found in tonic water, right? Strychnine, common pesticide used to kill rodents. And vinblastine, a very famous anti-cancer drug that's used for non-Hodgkin's lymphoma. And this thing, look at that molecule, look at that structure. It's so complicated and so beautiful and intricate. And this is made by the Madagascar periwinkle plant. I don't understand why the plant needs to make this molecule as complicated as it does, but I'm glad it has done that because it is incredibly valuable to humans. Okay, so I'm interested in not these alkaloids, but I'm interested in other alkaloids that you've probably not heard of. They're well known within the chemistry community, but not necessarily to the general public. And these are called fused bicyclic alkaloids. So if you look up on the top row, all those structures in blue, you got 2 hexagons stuck together, and you have a nitrogen atom in it. On the bottom row, you see these pentagon and hexagon stuck together with a nitrogen in it. And these molecules have a wide variety of medicinal properties, just like I showed you on the previous slide. They go everywhere from anti-cancer to lowering your blood pressure to preventing blood clots, reducing pain. There's a ton of medicinal properties here that we could exploit. So what if you could come up with a method that you could basically make any of these molecules or any other molecule that contains these core structures? The idea being that you could derivatize these core structures with all kinds of different groups, and you could make libraries of potentially medicinal compounds that you could screen for biological activity. And so that's what we've been working on. We've been working on doing this. And so in graduate school, I got into some nitty-gritty details with certain molecules, and this is one of them that I got interested in. It's called Oxazol. It's a little pentagon molecule that has a nitrogen, an oxygen, and 3 carbon atoms in it. And there are so many ways of making these molecules. There are many that are commercially available. There are hundreds that are available from chemical suppliers. And this has a long history of chemistry and organic synthesis. And so here's 2 books I have in my office right now that are just about the chemistry of oxazoles. Okay, so these things are so readily available and so well studied. I didn't think that I could really kind of use this because this is so well studied. I didn't think I could make any contributions in this area. But it turns out that if you just do one chemical reaction with these things, you add an extra group onto the ring, it turns it into this thing called an oxazolium salt. And these are much less common in the chemistry community. There aren't a lot of people studying these things. In fact, the only people that have studied these things are either retired or dead. So I'm pretty much got free reign of this area and looking at these oxazolium salts. And they have completely different chemical and physical properties. Okay, you can do all kinds of new chemical reactions that you couldn't do with oxazoles in the past. And so we thought we could use, there's that little nitrogen in the oxazolium salt there, right? We thought we could use that to install the nitrogen atoms in our alkaloids that we want to make. So we came up with a general plan for doing this, and we take our general product, we can make that from an oxazolium salt, and these oxazolium salts can be made from simpler chemicals called acid chlorides and isonitriles. And I thought this was a really good plan because this is easy chemistry to do, but there was one thing I was really worried about, and that is this chemical on the end, the isonitrile. If you read about this chemical in the literature, you read some of the most horrifying things about these molecules. Here's just one quote from the Journal of Organic Chemistry. They say that isonitriles are the Godzilla of smells. You can't believe how awful they smell. They make you want to vomit your guts out instantly. Right? In fact, they've used this in non-lethal weaponry. So I'm thinking to myself, college students working with non-lethal weaponry. Not sure if that's going to be a good idea. But it turns out that when we make these compounds, they don't smell at all. They're stable solids. We can weigh them out on a scale, and they behave perfectly. So we were thrilled with this because we came up with a way to do this, and you can do it in one afternoon in the lab. So an undergraduate can come in here, make these precursors. We've made libraries of these compounds. We've had probably over a dozen now that we've made. And you can take them and next day in the lab, bring them in, activate them, and you can produce these pentagon-hexagon molecules that are stuck together. And so we've made probably about 10 of these molecules. We published this in the Journal of Organic Chemistry a few years ago, and now we're working on expanding this reaction and using it to make all those other types of alkaloids that I showed you earlier. And so we can change the ring sizes. We can make, instead of hexagons stuck together, we can make 2 pentagons stuck together, or we can make a pentagon and a heptagon stuck together. And we can change the overall structure of the molecule, and that will change their function. They will have different properties from the other ones. We can add layers of complexity, build more rings onto them, and make them look more like those alkaloids that you isolate from natural sources. And so we think we can make a big impact here on health because we can provide a bunch of drug-like molecules very quickly that can be screened for a variety of different diseases. And so that's exactly what we're going to do. We're planning to make these molecules and send them off to the NIH, and they have this molecular libraries program where researchers across the country can submit their compounds, and they'll put them in little plates with hundreds of other compounds, and they'll send these plates out to different research centers all over the place, and they will screen these against every drug target that they can come up with. And so, in the pharmaceutical industry, there's a term called 1 in 10,000, and this term is meant to imply that for out of every 10,000 molecules you make, one of them will make it to the clinic, right? So to clinical trials. And so you need to screen as many molecules as quickly as you can. And so if we can provide more molecules more easily, then you can help the pharmaceutical industry produce drugs faster and cheaper. And so that's exactly what we're going to do. I have professors that I had from graduate school have submitted compounds to this program, and some of them have been screened over 900 times. And so that's what what we're hoping to do in the near future. So I hope I've given you kind of an idea of what my priorities are in terms of research. Number one priority, of course, is training students for careers in science, but also providing tools for biologists, for biochemists, and discovering and designing new reactions that can aid in the pharmaceutical industry. And so that leaves me just to thank a bunch of people. I want to thank my current group members, Sam and Ajua, who are actually doing research right now, so they are not here today. I also want to thank all the past members of my group. You can see where they ended up after they've graduated. I have a bunch of collaborators that I've been working with for a number of years. I want to thank the funding agencies for helping us out. And I want to thank all of you for coming out today and listening to me. So thank you very much.
So really nice stuff. So let's say that you come up with this molecule cures migraines and poverty and world peace as well. It's fantastic. So is there an issue? So the work that you're doing now is on a small scale. Are there issues to scaling up this production that are challenges?
Yeah, there are always challenges in that. So that's an entire field of the pharmaceutical industry called process chemistry. And the job of a process chemist is to take something from the small scale and scale it up to the point where you can make multiple kilograms of these compounds so that you have enough supply for patients. And so that is, I have a few friends that are process chemists, and they love it. These are the types of challenges that they eat up. Okay, they will go in there and they will fix reactions until they are 99.9% yield and no impurities, and you can the products just crap out, and you can filter all this junk away from it. So that's a great question, and it is definitely a part of the process. And so we're making milligram to gram scale molecules here. And that's about all we can do in our laboratory, but that's the next step for any compound that would go into the pipeline. Yeah.
Okay, so you're looking at two different classes of molecules, the alkaloids and the brain stuff. Yeah. Which one do you think will have the biggest impact? So you have undergraduate students slaving away in the labs, right? And so these are two different type processes. What direction is your lab going on? Is it equal, or do you see one having a bigger contribution than the other?
Well, the migraine project really came out of Victor. I mean, he was the one that got us started on that. He needed the compound, and I thought I could train some students, and they got really interested in migraine drugs. And so I think that project will probably kind of go to the sidelines, and we're going to focus on making the libraries of alkaloid compounds. And I think that those are where we're going to see how far we could go with it. So I have not filed a patent on the method for making them. So I want people to use my chemistry, and I feel like if you have to pay a royalty, you're limiting people and also making money off of process patents is very difficult anyway. But if we submit a compound to the NIH, and let's say by some miracle we actually get a hit, the NIH will let you know, and you'll have a year to file a patent. And so they allow you that ability, which is another great thing. But of course, you have to move fast because everything you do with NIH is public. And so if somebody sees you have a hit, right, they might look at that and start going after that as well. And I can't compete with Merck or Pfizer or anybody like that. I'm not trying to do that, right? I'm just trying to enable those people to do their work more easily. All right, thank you very much.
Thank you all for coming out to the faculty presentation component of today's activities. We sure appreciate the energy from all four of our great speakers. They represented each of the schools in outstanding fashion. Thank you all for attending. We look forward to having you at next year's event, and please join us in the atrium for the showcase component of today's activities.